I will introduce you. Next speaker is Professor Chen. Her title, presentation title is Complex Transition Metal Hydrides. Please.
Yes, thank you. I'm sharing my screen. Can you see my screen? Can you see?
Yeah, next speaker is Professor Chen. She is coming from the Dalian Institute of Physical Chemistry, Chinese Academy of Sciences. Welcome.
Thank you. I'm sharing my screen. Can you see that? Can you see my screen?
Yes.
Okay.
Yes.
Okay. Yeah. Yeah. Good morning. It's my great pleasure to be here, and I am really grateful for the invitation from Professor Chen and also the local organizing committee for this wonderful event for me to join. And it is 5 years before that in Xiamen University that also Professor Chen invited me to be there, and that was the first time I got in touch in the fusion research. And because of hydride is the material we have been working for quite a long time, but of course we are not in nuclear fusion area. We are in the chemical reaction, but hydride somehow has a lot of properties that can be in chemical reaction, can be nuclear reaction. So since 2016 from Xiamen, and it's just very nice for me to sometimes I just want to bridge like chemical reaction with nuclear reaction, that somehow we have a hydride in between. And I told with my students that please do keep an eye on your materials when you conduct thermal reaction or conduct plasma reaction. What could be some abnormal phenomena observed? So that's I think this is a really attractive, and for me, although I'm still very preliminary in this area, but I really enjoy this ongoing events in this very important field. And I think earlier this year, when Professor Chen sent me an invitation, I thought I won't focus on my own research on hydride for hydrogen storage or catalysis, because I am now majority of our research group in these two topics. And instead, I would like to pick up a few things that we have observed during our research under some unique properties of transition metal-based hydrides. So today, I'd like to share some of the results and some of the background knowledge with all of you, that we could somehow have some kind of information that probably would be of some interest. So here's the content of my talk, and I'd like to introduce the complex transition metal hydrides, and then I will pick up 3 cases for to show that what's the chemical properties of these hydrides in our daily research, and what could be possibly be of interest to maybe to nuclear reaction. And first of all, people in hydride community normally refer hydride as material contains hydridic hydrogen. But in a broad sense, we can divide hydride according to their bonding nature. So we have ionic hydrides, we have metal hydride, we also have covalent hydride. For example, water, methane, and ammonia. Those are covalent hydride. And we know that those hydride, in some cases, they have mixed properties. For example, when some metal hydride complex with ionic hydride, they are from complex metal hydride. I will talk later. And for the this slide shows that for some of the covalent hydrides like ammonia, methanol, and methane, those are very promising chemical energy carrier. So people in this area probably know that there's strong pushes by using ammonia or methanol as a hydrogen carrier for the clean energy utilization. So this is for the most cases in the covalent hydride. And for hydrides, there's many other applications. And for, of course, for metal hydrogen storage, hydrogen storage research has been carried for more than half centuries. And we can see that we have a lot of metal hydride and complex hydride for the purpose of hydrogen storage. For example, nickel hydride is an interstitial hydride. And we also have complex hydride like sodium analyze. And instead of hydrogen storage, those hydrides can also be used for the solar thermal energy storage. And for example, you can see titanium hydride and magnesium iron hydride. Those are very stable hydride. They can be used as a high temperature hydride and combined with a low temperature hydride. For this combination, this hydride can store solar thermal energy. And this also be a very promising research topic. Also, this hydride contains small cation and anion, such as lithium ion, sodium anion, sodium cation, and also in some cases it's hydride anion. And in some cases, in some materials, those small ions can be transferred in the lattice, so they can be electrolyzed. Those are also a very interesting topic. Also, people also, I think most people are aware of the very good, very attractive research on superconductor. For example, the lanthanum hydride system, they can achieve high temperature superconductivity. So this is also an interesting topic in hydride community. And instead of this, I also like to bring you to this slide, is that hydride can be in solution phase. For example, if you look at the left bottom, you will see that we have a hydride complex from iridium, from titanium, from ruthenium, from iron, etc. Those are very good catalyst to hydrogenation reaction in liquid phase. So it's a homogeneous system. We also have hydride in play in biological system. For example, in nitrogenase, we have ion hydrogen environment, which is very useful as a precursor to activate dinitrogen. Of course, in solid states, those hydride, some of hydride have been used as catalyst for the chemical conversion, like in ammonia, we use some hydride as a catalyst from dinitrogen to hydrogen to ammonia, and we also can use carbon dioxide as reactant and convert it into methane or methanol. So those are a lot of type of hydrides that has been used or investigated in chemical in chemistry or in catalysis. And today our focus is on complex transition metal hydrides, and this is kind of this is kind of a subgroup hydrides. If you look at the general formula, it is like a hydrogen bonded with transition metal from an anion. And this anion complex with cation made of alkaline earth, maybe sometimes rare earth cations. I will give a few examples here. The first one is uranium hydrogen 9. This is anion. It's complex with potassium. It's the very first complex hydride reported by Sweden scientists in 1964. And then we will have magnesium nickel hydride. This is very important hydride for hydrogen storage. This was reported in 1986. And I also like to bring your attention to the lithium palladium hydride. It was reported in 1989. And in this hydride, you will see that the palladium is in 0 valence, but hydrogen is covalent bond with palladium, and they form anion. So this is could be I think could be the very first palladium hydride, if I remember correctly. And later on, we have a number of ternary and even quaternary hydride reported. And from this reference I highlighted here, there's many hydrides that's reviewed in this this book chapter. It's really informative. If you're interested, please refer to this one. And accordingly, by year 2005, there's over 127 complex transmetal hydride reported. And now I think could be much more than that. And so this is the coordination geometry of the complex transmetal hydride. You will see that the black ball represents the transmetal, and the small white small ball is hydrogen. Those are hydrogen. You will see that we have there's actually more than 8 geometry. I just pick up 8 of there. You can see that the transmetal can bond with 9 hydrogen, 7, 6, till maybe here in the complex hydride system, we can have also 2 hydrogen there. And some of them are represented by palladium-based hydride. So there's quite a number of possible arrangements between hydrogen and transmetal. And these anions, has to be stabilized by cation. So the cation play a very important role in stabilizing those structures. Now here is the properties. I just collect these things to share with everyone, because I also learned something from her. I also learned by myself the information generated by numerous effort from community. And I will say that because we have alkaline earth as a cation, and we have this anion, most of the hydride are non-metallic, with several exceptions that a few are metallic. And of course, most of them are highly reactive with water and oxygen because of chemical driving force. And we can, as I showed before previously, that the hydrogen to metal ratio could be very high, up to 9. So this is very different from the conventional transition metal hydride. Normally, we won't have such a high hydrogen to metal ratio. And in some cases, especially for the late transition metal, the apparent oxidation states of the transition metal is somehow near 0. Of course, the cation play a very important role in stabilizing those complex hydrides. So regarding to the synthesis, there's a few ways. I just pick up 3 representative ways. One is by choosing a different mixture of the alkali earth hydride with transition metal, mix them together and heat them under high hydrogen pressure. Or you can start with alloy, or with a mixture of alkali earth hydride with transition metal, also calcination at temperature and pressure. You also can apply ball milling. You also can do metathesis. And I'd like to highlight one thing here, that the hydrogen content in the complex hydride would somehow depend on the pressure applied in some cases. For example, for sodium palladium hydride, if you have this synthesis condition around 300 degrees Celsius and the pressure of 100 bar, you probably have sodium 2, palladium hydrogen 2. But if you apply extremely high pressure, like 1,800 bar, you probably have a palladium hydrogen 4 there. So hydrogen pressure is critical in determining the oxidation states of transition metal. And particularly, I'm just list a few palladium-based complex hydride here. You can see that palladium can bind with 2 hydrogen, 4, 3, or between 2 and 3. So this combination gives you different structure and different valence states of palladium. And I'm also listing here is the other palladium hydrogen bond lengths here. You can see that if you use alkali metal, you will have shorter palladium hydrogen distance. But if you use alkaline earth, you will have a longer one. And as far as know that the hydrogen distance somehow is not is somehow longer than those in palladium hydride, neat palladium hydride. But the palladium hydrogen distance is somehow shorter. So those are the some background information of the complex transmetal hydride. And now I would like to mention a few systems that we have encountered in our daily research. First of all, I'd like to bring to the lithium palladium system. As I mentioned before, that their lithium 2 palladium hydrogen 2. This is this hydride was reported in 1989. And it is thermodynamically stable, and you can synthesize this material by making hydrogenation, by hydrogenating lithium palladium under a certain temperature. And this is structure. And I'd like to show what we observed during the synthesis. Well, we use lithium hydride and palladium. We mix them together, and we heat the mixture without hydrogen pressure until temperature above 350 degrees Celsius. We show some transitions. That is that at temperature around 140 or 100, about 130, we saw the formation of lithium palladium hydrogen 1. This is we can regard it as interstitial hydride. But at a higher temperature, around 180, we see the formation of complex hydride lithium 2, palladium hydrogen 2. So that means that this complex hydride can be facilely synthesized by heating palladium with lithium hydride. And this is this formation. However, under inert atmosphere, this lithium 2 palladium hydrogen 2 decompose to the interstitial hydride, then back to lithium palladium alloy up to 350 degrees Celsius. So this heat treatment, it forms and decomposes. And I would like to show what this means, what it means for our research, especially for the nitrogen fixation. We notice that when we put palladium into lithium hydride, when we mix mixture, we can efficiently fix dinitrogen into our material. And you can see from the red curve here is that the TG, nitrogen TG, you will see the weight gain start at earlier at lower temperature than the other samples, which shows that the lithium palladium hydride probably catalyze the nitrogen fixation reaction. And we did observe that after nitridation, we have the nitrogen hydrogen bond stretch here. So combined with in situ X-ray diffraction, we know that lithium palladium hydride is very highly likely to behave as a catalyst for the dinitrogen fixation. So that's give us a very interesting, very good idea that we should use this complex hydride as a catalyst to fix dinitrogen. So by doing so, we are able to achieve pretty high nitrogen fixation rate as well as ammonia production rate by adding palladium into the hydride system. So the lithium palladium hydride would be a very good candidate to catalyze ammonia formation. And then I'd like to move on to the calcium palladium hydrogen system. For this system, I'm not going to talk about nitrogen fixation, but I'd like to talk about hydrogen content at the surface of complex hydride. For this calcium palladium system, the most stable state is calcium palladium hydrogen 2. And we also have palladium hydrogen 2 units in the lattice. There's another structure, is hydrogen content more than 2. And people trying to make calcium palladium hydrogen 3 we want to increase hydrogen content in the system, but it's very difficult. If you look at this isotherm, the vertical, the y-axis is hydrogen pressure, and this the y direction is hydrogen content. It is very difficult to achieve hydrogen content higher than 2.6. So that is in back phase state. However, in collaboration with Professor Wu in Xiamen University, we found a very interesting phenomena. What is that? That is that if we look at the surface of calcium palladium hydrogen 2, and we added hydrogen onto that surface, of course we have to encounter a 1.07 electron volt kinetic barrier, but we could have a state, that surface state with hydrogen-rich surface, and this is information that motivate us to think that, and at the surface, the chemistry, the driving force for chemistry would be somehow different from the back phase. As Professor Chen mentioned before in the opening remarks, we know that surface chemistry is very important for catalysis and for electrochemical chemical reaction. And for this calcium palladium hydride, the surface chemistry, the surface hydrogen content would be easily more than that in back phase. Although we haven't continued hydrogenation to even high hydrogen-rich surface, but if you compare the energy state of the starting state to the final state, this is not much, no significant difference in the energy state. Note that we run this at 120 degrees Celsius and low hydrogen pressure. So if you apply high pressure, the driving force will be even stronger. And so this study, these results give us remind us that the hydrogen at the surface could be could be more than we can expect it, because in heterogeneous catalysis in our field, people all know that there's hydride on the surface, but it's very difficult to identify hydrogen content, hydrogen species, hydrogen chemical environment. However, there's many unknown things means that we can explore more. So this is another observation we have for the complex system. And I also like to mention one more case is lithium-ion hydrogen system. This system is very interesting because if you look at the back phase synthesis, this is from people from Professor Orima's group from Japan, and they synthesize this material under ultra high pressure. If you look at the X-ray pattern, you will see that at 900 degrees Celsius and at 9.7 gigapascal, we can have this lithium-ion hydride formed. So this is very, very difficult. And we look at this structure, we have 6 hydrogen coordinated with ion, and we have lithium in the lattice. However, we have an abnormal observation is that when we mix lithium hydride with ion, we use this as catalyst. We found that this mixture can catalyze ammonia very well. And at that time we were very much want to know that what happens on the surface, because it's a mixture. We cannot see any new phases there. So we conduct a temperature program desorption, and we did observe an hydrodesorption at around temperature of 300 degrees Celsius. This hydrodesorption is very different from neat ion or neat lithium hydride. So that's something very different at the surface. So we collaborate with Professor Jiang from the ICCP, and we use a laser to bombard on the lithium hydride ion mixture in vacuum. We use laser bombard on the sample, and we observe gaseous phase clusters. And those clusters contains, you can see that we have this lithium-4 ion hydrogen 6 and lithium-4 ion hydrogen 6. We have a variety of complex hydride species in the gaseous form. So that means that for those hydrides that's not thermodynamically favorable under normal condition in bulk phase, but we probably can have this in the but we do have this in the gaseous phase, and this gaseous phase probably can give us idea that those species probably have a chance to form on the surface, because the surface have condition unsaturated states, and it resembles to some extent to a gaseous phase state. So that means that for those lattice bulk phase unstable hydride, we probably have a chance to form at the surface. And so that surface species, or we thought it could be surface species, but now we investigate in gaseous phase. We notice that this gaseous phase species are really reactive, are highly reactive with dinitrogen. It can dissociate dinitrogen into a amine group, and this means that dinitrogen can be dissociated and hydrogenated at the same time. So that reaction, that investigation gives us a very, very strong idea that at the surface, even if in bulk phase ternary hydride complex cannot be formed thermodynamically, we probably have high chance to form some complex hydride at the surface. And this complex hydride would have a unique role in catalyzed chemical transformation. So that's the information that we derived from the gas phase investigation. And then I think I am going to finish my presentation. I hope I could deliver clearly that the complex transition metal, they are very unique, and they now people are looking at this material as energy storage material, for example, thermal energy storage, cation storage, and now some people are looking at the catalysis. And we know there's a lot of things we need to explore, and especially surface. The surface of this complex hydride could be very interesting. And I also want to emphasize that there could be more hydride to be formed in near future, because previously this kind of research is not that many people in this area, but I believe more people will join this topic. And also we need to explore preparation condition that under mild condition. For some of the hydride, ultra high pressure has to be applied because of thermodynamic reason. But somehow we can look at the metastable states that synthesis could be conducted under mild condition. And I also like to also highlight here the most important things I want to deliver is that because palladium hydrides of focal interest in nuclear fusion, and as might mentioned before, that people are looking at hydrogen palladium content ratio as high as possible. And the things here that so for the complex transition metal, complex palladium hydride, the hydrogen palladium ratios could be high as 4. Of course, that's a very different hydrogen state as compared with neat palladium hydride. But this is something that very different, because we have lithium, we have calcium, have sodium here. We can stabilize these complexes. And also, but also I want to make here that in 1989, Professor Freshman and Porn, they conduct this reaction in lithiated system. So I'm wondering that whether lithium, oxygen, nitrogen, etc., would be somehow involved in this nuclear reaction. And of course, this is just on my not that fixed, but it's really want to make some connection here. And also, this very limited investigation on this transition metal complex hydride and the electrochemical condition. So that's all. That's really interesting, and I'd like to hear from audience that what's your opinion on this type of hydride, and what's a possible application of the hydride in nuclear reaction.